All right, see if we can wrap up this chapter here. So, the sun is not being particularly helpful here. Get some glare here. It looks like it's still okay to see there in the shady parts. So we'll see. We'll do the best we can here. So we were talking about size of ions there in the last video, and we hit this problem here where we want to arrange the following in order of increasing size. So we've got potassium cation, sulfide anion, argon, calcium cation, and chlorine anion. So an important aspect here is to recognize these all have the same electron configuration. So for argon, argon ends at the end of the 3p. So argon is 1s2, 2s2, 2p6, 3s2, 3p6, right? And so are all the rest of these. Potassium is one more electron than argon, but that electron is removed to make a cation. Calcium is two more electrons than argon, but two of those have been removed to make the cation with the +2 charge. And chlorine has one added electron, and sulfur has one added electron. So the key here will be nuclear charge. The higher the nuclear charge, the smaller this ion will be. The lower the nuclear charge, the larger this ion will be. So let's just identify the number of protons in each of these. That'll help us figure out who's got the higher nuclear charge. So argon is 18, potassium is 19, calcium is 20, chlorine is 17, and sulfur is 16. So the biggest nuclear charge is for the calcium. That means the electron cloud of the calcium will be constricted the most. Calcium dication will be the smallest. Right? Next would be potassium cation. Then argon would be in the middle. Right? Then the chlorine anion, and then the sulfide anion would be the largest of these. So keep that in mind, right? When you're making ions, could be a case of you're changing the electron cloud. Right? But it could be a case that they're isoelectronic, meaning they have the same electron cloud. The difference is then going to be the nuclear charge, or the charge, positive charge on the nucleus. Okay, one more page here, and nature is not really helping a lot here with the shade that I'm getting here. So let's try to keep it in the shade, so at least it's uniform. Another property we want to think about is called the ionization energy. And this is the minimum energy required to remove an electron from an atom. So let's think about how that would vary with the periodic table. So again, let's take a picture here of the periodic table and try to evaluate what's going to happen. Right? We're trying to take an electron away. So again, let's start with going down. Right? And imagine we're trying to take an electron away from, say, a lithium. Right? That electron is in a 2s orbital, so it's pretty close to the positive charge of the nucleus. So we go to pull that electron away, that electron still experiences the positive charge of that nucleus pretty strongly. As we start to go down that column, we go from lithium down to sodium, we're adding an extra layer of electrons in between the outermost electron and the nucleus. So lithium is in the 2s, sodium is in the 3s, potassium is in the 4s, rubidium in the 5s, cesium in the 6s, etc. So as we go down, the electron we're looking at removing gets more and more shielded from the positive charge of the nucleus. So even though the nuclear charge is going up, right? We're having more and more protons in the nucleus. That electron is experiencing less and less of that charge. So the ionization energy is going to go down. It's going to be easier to take an electron from a large atom like francium or cesium than it is to take electrons from a small atom like lithium or sodium with a similar configuration. So ionization energy is going to decrease as we go down the periodic table. Now, what's going to happen as we go across? Okay, so again, we can use the same analogy here. We go from lithium to beryllium to boron to carbon across to fluorine. Right? The electrons are all going into about the same energy level. Right? It is the same energy level, different sublevels within the second energy level. But the other change is the nucleus. So we're trying to take an electron away from lithium. That electron is held by the power of 3 protons in the nucleus. But by the time we get over to fluorine, that electron, still in the second energy level, is now held by 9 protons in the nucleus. So as we go across the periodic table, it's going to get harder and harder to take that electron because of the increase in the nuclear charge. So ionization energy is going to increase across the periodic table. Again, because of nuclear charge, same reason why the atoms got smaller. Okay? So if we try to compare this information to evaluate some different elements, right, which has a higher ionization energy, right? Another way to say that, which one is harder to take an electron from, sodium or rubidium? Well, sodium and rubidium are both in the first column. So as we go down, it's going to be easier to take that electron hanging way out in that last sublevel. So the higher ionization energy is going to be sodium, because of the shielding that's present in the rubidium. Right? Nitrogen and fluorine are in the same row across the periodic table. So in both cases, we'd be taking an electron. I don't know if that's showing up on my video or not. In both cases, we'd be taking an electron from the 2p, but fluorine has more protons in its nucleus. So fluorine is holding on to those electrons more tightly. So fluorine would have a higher ionization energy because of its stronger nuclear charge or higher nuclear charge. Right? Now, selenium and tellurium, they are in the same column. They are here in the column of oxygen, column 16. Tellurium is below selenium. So as we go to tellurium, there are a whole lot more electrons that are added in that are shielding the outermost electrons from experiencing the charge of the nucleus. So it'd be easier to take an electron from tellurium than it would be from selenium. So selenium would be the answer, and the explanation would be the extra layers of shielding that are added in as we build up the electron configuration of tellurium. Okay, last periodic property we want to talk about here in this chapter is called electron affinity. This is the energy change when an electron is added to a gaseous atom, right, and it's in per mole units. Now, one thing interesting about electron affinity, it's not quite the same as the others in terms of how we think about it. In fact, I like the problem here as a way to kind of evaluate electron affinity. What we're thinking about is it better, right? Is it better energetically to add an electron to an atom, or isn't it? And what does that tell us about that electron's structure? So I kind of like to think about electron affinity in terms of this anomalous type of question. So basically, I just give some electron affinities here. Explain the anomalies in terms of electron configuration. Right? Now, keep in mind what we know about enthalpy. This is a negative value. That means it's an exothermic reaction. So that means that's energetically favorable in terms of what is happening. So the general trend here looks like they're getting more negative as we go across, right? And that kind of matches with what we saw with ionization energy, right? The higher nuclear charge, generally, that's going to be better able to pull in an additional electron, right? So electron affinity is not quite the opposite of ionization energy, right? Taking an electron, giving an electron, but it's in the ballpark of that. So the general trend is these are getting more negative as we go across. The anomalies then would be beryllium is positive. Right? Beryllium doesn't want an electron. Right? It's not exothermic to give beryllium an electron. It's endothermic. We've got to force the electron in. The other one would be nitrogen. So how are we going to explain these anomalies? So let's start with lithium and think about what happens with lithium, and then maybe we can see where beryllium might be different, so as that's not a negative value. Neutral lithium has an electron configuration of 1s2, 2s1. So if we add an electron to it to make it negatively charged, that would give us an electron configuration of 1s2, 2s2. So we're putting an electron into the 2s sublevel, and that's still an exothermic process. The lithium can pull in that electron. What's different about beryllium is beryllium already has a second electron in its 2s sublevel. So to add an electron to beryllium, we have to put that electron in the next highest sublevel. So beryllium with an added electron, that electron would have to go in the 2p sublevel. And that's the difference here. It's going to cost us energy to force an electron into the 2p sublevel because that electron is not pulled in as strongly by the nucleus because it's in a higher sublevel, higher energy sublevel. It's more shielded from the pull of the nucleus than, say, the electron we added to lithium or the electron we add to boron. Once we get to boron, there's already one electron in the 2p. The electron we're adding is still going into the 2p, right? And that may explain why this is a lower value than 60, but it's still negative because it's still pulling that electron in. Now, as we go to carbon, higher nuclear charge, it's even easier to add an electron into the 2p. What's different about nitrogen? So nitrogen, 1s2, 2s2, 2p, right? Nitrogen's atomic number is 7, so 3 in the 2p, right? Now with carbon, 1s2, 2s2, 2p2, the 2p sublevel for carbon would look like this. It's only got 2 electrons. The added electron is going to go here. It's not going to have to deviate from the spin of the first 2 electrons, but for nitrogen, the 2p is now half full. So all the electrons have spin up, but to force an electron into nitrogen, that electron is going to have to break the spin symmetry. It's going to have to go in with spin down. That's why it's not favorable. That's why we would have to force the electron in because of the spin. Go to oxygen, we've already broken the spin parity. We have 1 electron that would already be in there that is spin down. So the positive charge of the nucleus can pull in the 5th electron, right? And that gets even more likely for fluorine. So in terms of electron affinity, right, I think it's often useful to think about, right, how does the electron relate to the existing structure of the atom? Okay, and I think this is the kind of question I would want you to answer to, where you're actually going to have to kind of get your hands dirty explaining what's going on, as opposed to maybe the examples up here where you're just picking one, right? I really am going to want to see you explain what's happening and how the electron configuration and the other properties relate to that particular property. Okay, that wraps up chapter 7. Keep your eyes open. Chapter 8 will follow before too long.